Okay, so the first thing is that on these problems aren't really designed for no calculator. Some of them are very easy to do without a calculator, but if you get stuck, know that you can use your calculator on the book problems. On the assessment I give you, it will be, one or two questions, and you won't have a calculator. So the numbers will be structured so that they would be a little bit easier. So some of these you might want to have pulled out your calculator. So let's look at number 19. So number 19 says f of x is 2x to the fourth minus 3x cubed minus 6x squared plus 5x plus 6. And the question is, when is this less than 0? So we want to know when that's less than 0. So the steps are, as always, that we're going to find the zeros of it, and then we're going to look at the end behavior, and then we're going to figure out between the zeros what's going on, and when is this function less than 0. So if I didn't have a calculator, I would look at the p and the q. So the p is off of the 6. We're saying p could be plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6. And q can be plus or minus 1 and plus or minus 2. So the possible rational roots are going to be plus or minus 1, 2, 3, 6, and also 1/2 and 3/2, all plus or minus. Now, if you have your calculator, feel free to plug it in. I wouldn't give you one where you have to spend the entire time on the quiz guessing in these, but we'll take a very good guess here. I would say you want to probably try one of the middle ones, maybe 2 or 3, because I know what the answer is. I'm going to try 2 first. So we'll just plug in synthetic division. We'll plug in x equals 2. So we have 2 times 2 is 4, minus 3 plus 4 is 1. 1 times 2 is 2, minus 4, minus 8, minus 3, minus 6, 0. Right? So we have one of the zeros already. So if we go on and say, all right, well that function then has now become x minus 2 times those remainders that I had there. I have to go back and look at them. Go back. 2, 1, minus 4, and minus 3 times 2x to the cube plus x minus x squared minus 4x plus 3. Oh, minus 3. Okay. So now we would have to factor this one, doing the same thing. We'd have to get the factors, and we're basically trying to find the zeros. So at this point I'd say, you know what, this is a long process because now you have to factor this cubic function. And we would have to say, okay, what are, I got to change this, this is a negative, sorry. This is a minus 3 from my problem earlier. So what are the factors of this? And we'd say, okay, p is 3 and 1, q is 2 and 1, so we'd have to find the next factor. So go ahead and graph this one and see what it looks like. So when you graph this one, what you should see is that you're going to get a function that comes down and touches the axis here at -1 around here, goes back up, comes down and crosses here, and comes back up. So we have a 0 here. There's going to be a 0 here, and that 0 is at 3/2. So you could use your calc 0 function, and then there's a 0 here where it touches. So where is this function negative? Because the question number 19 says, when is this function less than 0? Right? Well, the only time that this function is less than 0 is when the graph is below the x-axis. Right? So the function's below the x-axis from 3/2 to 2. Okay. So graphically you could get that one very quickly. What this means is that if I was to continue factoring this, this would look like this. X minus 2 times x minus 3/2 times, it looks like it's an x plus, what that 0 is. So this would be an x plus 1 times x plus 1. This is going to touch there, right? So your 0 is a -1, -1, 3/2, and 2. and because the multiplicity of your 1, 0, the multiplicity of this 0, the negative 1, is 2, it just touches at the axis there, so it doesn't cross. Does that make sense? All right, so on 23, if we have the product of these two things, the first quadratic is an irreducible quadratic, which means that it has two complex roots. So these are not going to touch the axis. We won't touch our cross for these two roots. The other two roots are what, based on this function? We've got two other roots on this function. They come out of this. So what are the other roots? 3x minus 4 equals what? Right? We have to set that equal to 0. So x is going to equal 4/3, and that's going to be twice. This is going to have...
Not do anything about it being squared.
Right, because it's going to have a multiplicity of 2, because it's like 3x minus 4 times 3x minus 4. Okay, so what we have here is we have a function where we have two complex roots, and we have two roots that are 4/3. Right, if we go back and look, we have two roots that are 4/3, which means that if you have two roots, a multiplicity of 2 is a cross or touch. Cross or touch the axis if the multiplicity is even. Touch, right? Touches the axis, it doesn't cross. All right, and then if we go back and we look at this function is a squared here and then an x times an x. So what's the degree of this polynomial function? If we look at the degree, we have 2 here, and then we have 3x times 3x again, because it's squared. So I'm going to take 2x squared times 3x, and when you do that, the very first coefficient is going to be an 18x to the 4th. If I was to FOIL that polynomial out, I would get 18x to the 4th plus something, plus something, plus something. So my degree is 4, and my leading coefficient is positive, which means that this thing's going to have a shape like this. It has to go up. The end behavior is up in both directions. And what we just found from our roots up there is that on our graph, it's going to just barely touch the axis at 4/3. And if it's going to go up in both directions and only touch the axis there and have two complex, then the entire graph is above the x-axis. Right? So to answer this question says, when is this function positive? So this function is positive, right? When is f of x positive? That's from negative infinity to infinity. The entire function is above the x-axis. When is that function greater than or equal to 0? From negative infinity to infinity. Right? When is this function less than 0? Never. When is this function less than or equal to 0? At 4/3, yeah. So there's only one place that this function is less than or equal to 0, because it's equal to 0 at 4/3, it's equal to 0. So the way to answer this, and I'll just go on the next page to make this clearer, but so the question says, when is that function greater than 0? The function's greater than 0 from negative infinity to infinity. When is the function greater than or equal to 0? That's also from negative infinity to infinity. When is the function less than 0? The function's never negative, so there's no solution for that. And when is the function less than or equal to 0? Well, it's equal to 0 at 4/3. So that would be the answer. Before we start graphing it or anything, let's just take a look at what does it mean that the bottom has to be greater than 0. The bottom of the fraction can't be equal to 0, but under a radical can't be less than 0. So let's just start off by setting what's under the radical greater than 0. So we're going to say 2x minus 3 has to be greater than 0. Otherwise the function doesn't even exist. It's imaginary. So we'll add our 3 over there and we get 2x is greater than 3. So x is greater than 3/2. The function's not even defined below 3/2. Okay. Now, the next part that we want to do is find out when is the function 0? When does the function actually equal 0? Because that's going to be another piece that we have to worry about. So the function's going to equal 0 when what? What do we look at for equals 0? What part of this rational expression do we have to worry about for the function to equal 0? the numerator. So the function's going to equal 0 if x equals 5, the function equals 0, and if x equals 2, the function equals 0. Okay. So we know that those are both solutions because this is a greater than or equal to 0, and if equals 5, it equals 0. If it equals 2, it equals 0. And both of those numbers are bigger than 3/2, so both of those numbers are okay. So now the question is, what happens at those two numbers? Do we cross the axis and go to the negative, or do we not? So I'm just going to pause for a minute and go to the next slide. The function doesn't exist below this value, so we have to be at 3/2 for the function to begin. And then at x equals 2, we have a 0. Oops. And at x equals 5, we have a 0. So we're just going to put in a couple of numbers here. So at 2 and 5, we have zeros. So we'll do a sign chart in between these places. Okay. So let's do when x equals 3, right? When x equals 3, then x minus 5 is a negative, so we're going to have a negative. The absolute value is always a positive, so we'll put a positive there. And on the bottom, we're going to have the square root. The bottom's never going to be it's never going to be a negative number on the bottom. Right? So when you think about this sign chart, right, look at the actual function itself, and let's analyze the sign chart. The absolute value, this is always going to be a positive number. The square root of something is always going to be a positive number. So this function is only going to be negative when this thing here is negative. So this function from 3/2 up until 5, this function is negative. Right? Because when this is negative, the whole function is negative. So from 3/2 all the way up to 5, we've got something going on that we're below the axis. And then we're going to go above the axis because that x minus 5 is going to become positive after 5. And so the answer to this one is going to be that from 5 to infinity, we would be greater than, this function would be greater than or equal to 0. Number 57 says, consider the collection of all rectangles that have lengths that are 2 inches less than twice their width. Find the possible widths in inches of the rectangles if their perimeters are less than 200 inches. So let's say we have a width and a length. So tell me what is given in this problem. So we have perimeter equals 4w minus 4 minus 2w plus 2w, and that's supposed to be less than 200. Is that correct? Bringing it forward. Okay, so we have 6w minus 4 is less than 200. Subtract the 200 from both sides because it's just easiest when you have a 0. So 6w minus 204 is less than 0. And now graph that. So we're going to do 6x minus 204 is less than 0. So this is a linear function. When we graph it, we'll find that the 0 occurs when 6x equals 204, or when x equals 34. Right? So when w equals 34, that's when my function changes from being less than 0 to greater than 0, and we want the width to be less. We want the perimeter to be less than 200, so we need the width to comply with that. So for these x values, these w values, our perimeter is less than 200. So if we look at our w values, right, our w is x, this is w, and this is perimeter. So our w can be from 0 to 34. That's the 0 on this function. And so as long as the width is less than 34 inches, we'll get a perimeter that's less than 200. Okay, so the next one is a box. I like the next one, number 59. We're designing a cardboard box, and you have a rectangle, and the rectangle of cardboard is 12 by 15, and we make the box. If you've ever wrapped a box in like a shirt box, you have these corners. So if you cut those corners out and then you fold up these flaps, so we figured these are gone, and then you fold up those flaps and you just tape them, it makes a little rectangular box. So what is the length? Once I cut these corners out, what you can see here is that the inside rectangle, this is the bottom of the box. right? And then you fold up the sides. So what's the length of the bottom of the box if I call these little squares x by x? So this length would be 15 what? Minus 2x. And this width would be 12 minus 2x. And the question says we want the volume of the box in number 59. We want it not more than 100 inch squared. So we want the volume to be less than or equal to 100. Now when I fold that box up, it's going to look like this. This is going to be 15 minus 2x. This is going to be 12 minus 2x. And what's the height going to be? X. Right? So now I have a function because volume equals length times width times height. So if I go to the next page, we're going to have the volume, which is equal to 15 minus 2x times 12 minus 2x times x, and that's supposed to be less than or equal to 100. So subtract the 100 and you get 15 minus 2x times 12 minus 2x times x minus 100 has to be less than or equal to 0. Now, these numbers are like real world numbers. They're not going to come out to be nice even crossing points, so graph this one. Graph it and find the zeros. Right, when you graph this one, you're going to have a 0 somewhere before 1. You're going to have a 0 a little bit after 4. And you're going to have a 0 between 8 and 9, I believe, somewhere up here. Okay? And the graph is going to go like this. And we want the negative part. So the negative part of this graph is these x values here, up until that point, and these x values here. So those are the x values that I could cut out those little squares and have the volume less than or equal to 100 for those x values. All right, so what are the zeros? Did anybody get them? Yes.
4.19.
The x values are 0.69, 4.19, and 8.6. It would be easy to say, okay, x has to be less than 0.69, greater than 0, because you can't cut out a negative little square. And x has to be between 4.19, so greater than 4.19, and less than 8.6. But this is actually a problem. 8.6 is not a possible answer. All right, so let me just visualize what's going on. If we take this and we have a little teeny x, that means that we just have like a tie box. It's a really narrow height, right? If we have a really big x, that means we have a box that we've cut a huge square out of, right? And it's a tall box, sort of like a Yankee Candle type box-ish, right? Because what you're figuring is you had this cardboard and you're cutting out these little flaps to fold it up. But how big can those flaps be if this length is 12 and this length is 15? Yeah, you can't cut out more than a 6-inch square, because if you cut out a 6-inch square, you're going to just have a piece of cardboard you're folding in half. And so the answers on the graph are correct, but if I cut a square of 6 out of this side and a square out of this side, I end up with a little rectangular square of cardboard again. It's not going to be a box. And so the real answer is that even though these are true from the graph, I can't go up to 8.6. I can only go up to 6. And then those values of those little corners I cut out, those will make a box that is less than 100. Either it's going to be a really narrow, a really short box, because x is going to be less than 0.69, and you're going to have to wrap something that's really skinny in it, or it's going to be a little cutout that's between 4.19 and 6, and then it'll be a tall box. That make sense?